All right, guys, welcome back. It's good to see you again after that little brief interlude with Dr. Carr. Hope you guys had a good exposure to some of the fundamentals of lipids, their synthesis and catabolism in biochemistry. I know you touched on it just sort of quickly. Saw how that, in ways, we talked about the acetyl-CoA pool, is going to touch on central metabolism, and then broaden that view out into how lipids behave with respect to forming biological membranes, right? Okay, those ideas are going to become really important here really soon because the endpoint of where we're headed in terms of where all this sort of metabolism we've been talking about, at least from the point of view of energy production, converges on something that doesn't work without biological membranes and proteins that get embedded in it. Okay, but before we get there, let me just remind you again of sort of where we were coming as we sort of entered into this discussion of central metabolism, right? If you guys recall, we started up here, of course, with glucose, right? And we saw in glycolysis how we break glucose down through this set of 10 or so steps into pyruvate, right? And then how we ran the pyruvate dehydrogenase reaction to run that oxidative decarboxylation to then get us into this amazing cycle based on tricarboxylic acids, the TCA cycle, which ultimately then, as you saw, takes all those carbon equivalents coming up in here as glucose, right, and basically shreds them out into CO2, right? So the ultimate products of our pathway down here become CO2, and we haven't really seen where this comes from yet, and water, right? Okay. And we saw there's sort of two main things that biological organisms are after when they run these two critical pathways of of glycolysis, right, up here, and the TCA cycle, right? And those two things that ultimately we're after is, of course, like metabolites. We've seen that both in terms of my discussions of these intermediary elements, the things that get produced as glucose is being broken down, or as um, citrate when it's formed by condensation of acetyl-CoA with oxaloacetic, as it's getting broken down. Those intermediates get bled out for supporting biomass production for all kinds of important critical anabolism, right? So metabolites are an incredibly important aspect of what these pathways are for. And we've only been able to touch on that a little bit, but hopefully you guys are going to keep that in mind. Of course, the other thing, the main focus we've really been aimed at here is energy, right? One of the big points for running these pathways is, of course, extraction of energy from the stored potential energy in these carbohydrate sources so that all these other great things about life can happen. Okay. But if you think about it, up to this point, our energy output from these two pathways has really been kind of lame, right? When you really get down to it. Because if you recall, the energy we were able to produce out of glycolysis up to this point was what? Like, it was like 2 net ATP, right? And then out of TCA cycle, it's basically, per glucose, it's about the same. So, 2 net ATP. And that's just, kind of lame when you really think about it. I mean, for all that work, 20 or so reactions, we got 4 ATP out of it. And it's even worse than that, right? And it's a pain from a biochemistry student's point of view. That's a lot of chemistry and a lot of things to think about. And I got 4 ATP, but it's even worse, right? Because the average human being synthesizes on a daily basis about your body mass in ATP, right? So your body weight in grams at steady state, sort of average activity levels, you will synthesize about that mass of ATP per day. At this rate of ATP production, you're never going to get close, right? Not even in the ballpark, orders of magnitude away from where you would need to be. Okay, well, thinking about that, hopefully you guys then remember that those two net ATP from substrate level phosphorylation of these two pathways are not the only product of this pathway. In fact, from the point of view of energy related outputs, they're not even the main output of this pathway. The main output of these pathways is, of course, these high potential electrons that come flowing out of this pathway, right? Remember, we've got, 6 oxidation steps that take place in the course of going all the way through glycolysis and TCA cycle, right? There's 6 oxidations, if you recall, right? We've got, 1 in glycolysis at the pyruvate dehydrogenase reaction, right? We've got another one in the pyruvate dehydrogenase complex reaction, right? And then we've got 4 oxidations in the TCA cycle, right? All of that oxidation running these pathways per glucose equivalent is going to give us like 10 NADH molecules, right? And 2 FADH2s. So from sort of certain point of view, you could almost argue that's the major output of this pathway, the high potential electrons getting stuffed into the reduced structures of NADH and FADH2, right? And that's worth some serious energy when you really get down to it, right? So 1 mole of NADH, right? Think about this. 1 mole of NADH, right, is worth free energy difference, right, of minus 220 kilojoules per mole, right? Well, if you think about, you remember, right, that the synthesis free energy, ADP plus PI to ATP, that's going to cost somewhere in the range of about 31 kilojoules per mole standard state, right? Well, if you just do the division there, that's a lot of ATP. That 220 kilojoules per mole of NADH is worth the ability to make a serious amount of ATP, and we've got a whole bunch of that NADH to work with. That's the pay dirt, right? That's the big deal when it comes to energy production from these pathways, is making these high potential electrons that we're then going to use to make all of this ATP, because those electrons are worth so much free energy, right? Okay. The trick, of course, is understanding a couple of things. One, why is there so much energy in the reduced form of NADH? There's decent amount in FADH2, the less. We'll grapple with why that's the case in a few more lectures, another couple of lectures, next lecture. But so that's one thing we want to understand, is why is it worth so much free energy? Where does that come from, right? The second thing we got to come to grips with is, how do we extract that energy? How do we get at it, right? And what you're going to end up seeing is the answer to that second question, how do we get at it, has everything to do with aspects of the membrane biology that you guys just talked about, and essentially the design and exploitation of what, when you really boil it down, is an electric motor that is used to synthesize ATP, and that's powered by the free energy of the electrons, these high potential electrons that are present in NADH and FADH2. Okay, so to understand really how this all gets put together, one of the first things we have to do is think a little bit about that's this sort of free energy question. This sort of, why is it that these reduced nicotinamide or flavonoid rings have so much free energy in them? And from the point of view of free energies, the way we've talked about it up to this point in the class, I've mostly been talking about free energy with respect to things like hydrolysis free energies, right? Or combustion free energies, the kind of classical chemistry of bond making and breaking, right? Between carbon molecules, or carbon and oxygen, or carbon and nitrogen, right? Or from the point of view of weak interactions, like we talked about in terms of protein folding, right? Van der Waals interactions and things like that. That's really sort of where we focused our thinking about free energies. But now we're sort of in a different regime. Now we're in a situation where we've got to think about free energy from the point of view of moving electrons around, right? We got to think about why it is that pulling electrons into or out of the structure of a molecule like NADH is worth so much free energy. and uh, sort of thermodynamically why that's the case. So this requires us now to think about a certain type of chemistry, which I'm hoping you guys have remember a bit of, which is of course reduction oxidation chemistry, or for short, redox chemistry, right? And so understanding something of the free energies of redox chemistry is right at the core of why that energy is extractable in the way it is, and how we can ultimately then use it to make ATP. All right, so we'll get started on that in the next video.